Hi, everyone. So I'm Nicolai, and usually I dive right in and tell you a little bit about myself later. But today I want to do that a little bit differently because, let's see whether I judged that correctly. You see that guy? That's me. That was 1.5 years ago on the exact same stage, which actually pretty much the same topic, the Java module system. And I even put on the same shirt. It's a little bit less black and it has a little bit more pounds in it, but other than that, it's pretty much the same. So I was in Kiev. That time was the first big conference talk I gave, and I'm really happy to be back in Kiev again. It's not only a nice city, it's also a great conference venue. I was at a different conference back then. Okay, let's get going. I'm going to be talking about the module system, and I'm going to assume that you already know the basics, that you already know how to declare a module, how to compile one, and I want to show you the more advanced features. They're not really more complicated, but they're not ones that you will get in touch during the first small tutorials. And what I show you today is just one part of the module system, of course. There would be much more to talk about, but we don't have that much time. Last but not least, the slides are already online. If you go to slides.codefx.org, you will see them there. So if you want to follow along on your machine, you can do that. So I said I assume that you know the basics, but I still want to rush through them very quickly to get you up to speed. So modules. Unlike jars, modules have 3 essential properties. They have a unique name, they express their dependencies, and they export specific packages. And these packages make up the API. And this information is, you put this information into a module info Java, which then gets compiled to a module info class, which then ends up in a jar, which defines the module and makes it a modular jar that your module system can process. So the 2 properties, expressing dependencies and exporting packages, I'll look at them in turn because they're some important concepts that I will refer to later. So the first one is readability. When a module like this one, this case module A, says it requires B, then first of all, the module system will make sure that B is actually present at compile time and at runtime, and will let module A read module B. So that's the concept of readability, and we'll refer to that later. It's worth noting and remembering that concept because you will see it in the documentation over and over, and it's important to know that term. Readability means if some module requires another, then at runtime or during compile time, it will read that other module. And on top of that builds accessibility, which means one module will export specific packages, and then the code in one module can only access code in the other module if the type is public. It's the same as before. But new two conditions in Java 9 are the package needs to be exported and the first module needs to read the second. So readability is a precondition for accessibility. And this implements strong encapsulation, which means if you're developing a library or even a monolithic application of decent size, you now have the ability to mark clearly which parts of your API are supported and are maintained, and which parts you consider to be internal. So based on these very basic properties, the module system itself got modularized. You don't have to remember all of this. It just means, I just want to show you how the JDK got cut into a lot of modules itself. What you cannot see, unfortunately, is right down there is Java base, like the module that contains string and object and those kind of important classes. And up there you have java.se, which is the entire SE, Standard Edition API. And the compact module is actually not there anymore, so this is an old image. But you see SQL is here, for example, so if you want to use SQL, you would use that module. So the JDK got split up into modules as well. But we're not only having the JDK as in modules, but of course our own applications as well. So I want to show you a short example application that we're going to refer to later repeatedly. This example is about 2 years old. So every 9 months, it comes back into season. Now is the time. Jigsaw Advent Calendar actually makes sense. It's weird to present this around Easter, but hey, I'm not going to do more than one example application, one for each season. So this is a really, really, really simple application. It's maybe, I think it's even simpler than the usual other tutorial applications that you see because it does really nothing useful. It is a small advent calendar, and what that means is you have a calendar which has 24 calendar sheets, and each sheet knows which day of December it is and contains a small surprise. The surprise is an interface, and because with Java we need some indirection, so we need a surprise factory too. So a surprise factory there, and then we have two implementations. One creates quotes, the other creates chocolates, and that's it. That's the entirety of the application. So first of all, using the module system of application of this size is of course ludicrous. We're just doing that for demonstration purposes. So how does the code look like? All the classes are really simple. Like the surprise can return a surprise, and the surprise factory can create a surprise. It's very simple. The only code that is not totally trivial is the main function, which as you can see is not highly complicated either. We create two factories, put them into a list, and then we tell the calendar to create an instance with these factories. Then we get an instance back, and that instance can transform itself into text, for example, to be printed to the console. So very, very basic. With these classes, what could a module structure look like? I just picked this one. Again, if this were a real-life project, it would be one module, but it's not. It's a demo project, so it gets turned to 4 modules. The API, which is surprise and surprise factory, I put them into a module called surprise. And then we have a calendar module, which contains the calendar class and the calendar sheet. Then we have a factories module with both factories. Could be 2 modules, actually. And then the main code that I just showed you, it goes into Advent. So it's kind of orchestrating that stuff. And the arrows between those mark dependencies. And you can imagine why they make sense. So the chocolate factory implements the surprise factory. So it makes sense that the module containing the chocolate factory actually knows or reads the module containing the surprise factory interface. And calendar needs surprise factories to create itself, and a calendar sheet knows a surprise, so this relation makes sense as well. And because Advent has its fingers all across the place and all over the place, and creates chocolate factories and puts them into a list of surprise factories and handles the calendar, it needs to know all of these other modules. So we have this very simple module structure. What do the module descriptors look like? Likewise, very simple. On the very right, you have the surprise module, which uses no other module. You don't have to require JavaBase, because everybody needs it anyway. So it only exports packages. Now, regarding names, this is not a good name for a module. This is a great name for a slide, because it's short, which is why I picked it. In a real module, you would want to use this inverse DNS strategy that you use for packages. So it should be called module org codefx advent surprise, most likely, which means that a module name is often the same as a package that it contains, but that's not required. It just ends up that way usually. Okay, so that's surprise. That's fairly easy. Now, calendar is not much more complicated, but it does actually require another module. It requires surprise. And then factories is the same. You can hardly see the difference. There, see it? So factories is much the same, and Advent is a little bit different. It requires all 3 other modules, but unlike them, it's never called into from outside code. So it doesn't need to export anything. So it just looks like that. Now, if you're like me, you've never compiled code by hand. I did this for the whole Java 9 thing. I did this a lot. And I don't want to go through any of the details. I just want to show you that compilation and jar and launching is very much the same as it was before. Main difference is that the compiler understands modules and how they're put onto the file system. So you can actually say, like, all my modules are below the source folder, start with the module advent and compile it. And then we'll often see a module path. We don't need it for the compilation, because we don't need an external dependency. But you can see it when the application is launched, that we don't define a class path, but a module path. So the module system will turn everything it finds there into modules. And that's that. Those were the basics. I would now like to go beyond the basics and discuss features, as I said, that are more advanced in a sense that you don't initially need them to start with simple examples, but you can do a lot of nice things with these. If you have questions about any of these, I would recommend you just wave your hand and someone with a microphone will come over. And at the end of each of these sections, I'll ask whether you have questions. This way, we don't have to jump, the questions don't jump all over the place. We can just have your questions to the topics that interest you and that we just discussed. If you have further questions at the end, you can then come up after the talk. So let's start with transitive dependencies. Not all dependencies are really the same. First of all, you have a dependency because you need the code in that dependency, right? But the way you use them can be different. You may use that code only inside your own module. For example, let's say you use Guava immutable lists. You might only use the immutable list within your code. But there's another case. You could use immutable lists on the boundary of your code, meaning, for example, as a return value in a supported API. And transitive dependencies cover the latter. As another example, we'll use the application that we just looked at. So the calendar factory, which is in the calendar module, has a method create, a static factory method create. And as input, it takes surprise factories, which come from a different module. So that means everybody who wants to use calendar needs to read surprise. The calendar module is not really usable without reading the surprise module. So in the image below, you can see that Advent, for example, would have to read surprise in order to use this method. Otherwise, it could not use surprise factory. So surprise module is pretty much innocent here. It's just a random module, but it gets exposed by calendar. Calendar is exposing it, meaning it's using its types in its own API. Advent is depending on all of that. So if you're coding Advent, how do you find out which modules you add? You could type a couple lines of code, and then you can have the compiler tell you, you can't use surprise factory because you don't read that module. So then you go into your own module descriptor, Advent's module descriptor, and require that module, and so forth. But this try and error process is not the best way to do it, right? It's obviously manual, and it sounds like a lot of useless or meaningless work. And this is where implied readability comes in. We had talked about readability, and I'll show you in a minute why it's implied readability here. What happens here is that if a module A requires transitive B, it uses the keyword transitive in there, then the relationship between A and B doesn't change. A reads B just as usual. But any other module that reads A also reads B. That means A implies readability of E. Reading A implies reading B. That's what's called implied readability. So in the simple example we just looked at, that's pretty straightforward. Calendar will now require transitive surprise, which means Advent, which requires calendar, will also read surprise without requiring it. Now remember, the accessibility rules said that for Advent to read any types in the surprise module, it needs to read that module. It doesn't need to require that module itself. It doesn't have to say Advent requires surprise. It's enough if it says, if it reads surprise at runtime. And one of the other ways that a reads edge can come into play besides requiring it directly is, for example, implied readability, where now Advent ends up reading surprise without requiring it. So this is the essential use case for this, why this idea of transitive dependencies of implied readability was designed. But there are a lot of interesting further applications for this, and I want to show you a small example for each of them. The first one are so-called aggregator modules. Assume you have like a huge monolithic system that consists of hundreds of modules, but you might have certain subsystems. You might have a subsystem that uses like 10 modules, and it really only makes sense to use these 10 at once, or at least you have a lot of use cases where you use all 10 of these. What you could do, you could create a so-called aggregator module. This is nothing that the module system knows about. That's just a term that comes on user space. It's just a term we use, where you create a new module, which is totally empty. It does nothing, but requires transitive these other three modules. That means everybody requiring Advent Calendar will also read these other 3. So now if you have a part of your system, we have a dozen modules that most likely people will use at once. You can create an aggregator like this, and then people only have to require one of those. It's one possible use case. It also works the other way around, though. So you cannot put stuff together. You can help taking stuff apart. So let's say after a long time, you realize that factories, the module factories, got way too big. You want to make it smaller. You want to make one API module, and then one chocolate factory and one quote factory. You can just do that, right? You can just split one module into 3, you shuffle the code base, shuffle the code a little bit around, and then you update all your requires clauses. If you can do that, then you're fine. You don't need any of this. But maybe you can't do this. For one, it might just be a whole lot of work that you're not willing to do at the moment. But more importantly, maybe you're deploying, deploying your artifacts to Maven Central. Maybe you're not the only one using your artifacts. And if that's the case, then if you just stop delivering the factories module, things will break for your users. And that does not only work like that for a real library that you publish publicly, but also maybe for a library that you use internally within your company. As soon as you don't have control over the entire users of the entire user code bases of your library, refactoring module and module names can be a little bit tricky, and with this can help you. So if you decide to split up factories, you can leave the factories module intact. You just put out all the code into the sub-projects, you require transitive all of them, and you turn factories into an aggregator module. And now every user of factories that used to use the actual module with the actual code in there will now require an empty module, but thanks to these to implied readability, it will read the new modules. So that's a use case. You could also use it the other way around. If we at some point realize that splitting this application to 3 modules, 4 modules was a little bit stupid, we can instead merge all of the code into one module, into the Advent calendar module. And then because the other module names would be still around, we could require Advent calendar transitively. And it's the same mechanism again. Everybody who requires the old modules by name will now also read the new module by name, and code will still compile and run. Small caveat, people who just use the calendar or maybe the surprise module, which is just 2 interfaces, now depend on the entire application. So now people depend on a lot more code that they bargained for. And this can even help with renaming modules. If you realize that it should be called surprise factories, really, you just create that new module, move all that code, and have the old module depend on the new. So you get the point, right? If you change something about your module composition, you can leave the old name intact and require transitive all the new modules. This is not 100% fail-safe. There can still be problems down the road, but this gets you a lot further than just removing that module. So in summary, if A requires transitive B, nothing changes between A and B. A can read B just the same, but any module reading A will now also read B. And as I showed you, you can use it to make APIs more usable. You can create aggregator modules, and you can refactor modules in different ways. And if you want to read more about that, I wrote a blog post going into more details. And now I'm going to give you a minute to come up with questions. So somebody with a mic should be coming out to you.
Please say, what were the reasons for not implementing transitive behavior explicitly? Not explicitly by default. Why do you have to explicitly type transitive keyword?
That's actually a good question. I think it's not a technical reason, it's a design decision. And I think it's a good one. It means that you cannot accidentally depend on your transitive dependencies. As it is now, I can depend on, let's say, Spring. And Spring, as far as I know, uses OK HTTP. So I can start using OK HTTP even though it doesn't show up in any of my POMs or build files or whatever. So at the moment in Java, I can depend on my transitive dependencies. And it will always work, but it never shows up in the files that I use to manage dependencies. I have no control over the version, And any analysis will show that I don't have a direct dependency on it, at least analysis that works based on the POM. So I think it's actually a good decision that we have to explicitly depend on everything that we require. This actually goes a little bit against that goal, so it's a trade-off. If you're tired of depending on your transitive dependencies, you could technically just use requires transitive in your modules everywhere. I wouldn't recommend that, but that this way goes against the other goal. So the third rule of accessibility was you don't talk about accessibility. Oh, sorry, that was the first two rules. The third one is that you have to read that module, and this way you can circumvent that. More questions? I don't see any. Optional dependencies. So what I just said about transitive dependencies, that's a little bit a step back from this very strict readability and accessibility rules, is even more true for optional dependencies. So it lessens the purity of the system and improves its usability. So not all dependencies are equally required, right? Some are just needed for your code to function. If that module is not, or that jar or that class is not there, you just can't do anything. And this is what regular requires clauses are there for. But there are two other versions as well. You might write some code that maybe does not really depend on that code, but can use it if it's there. So if that code is not there, then you adapt and do something else. And then the last part, the third point, is maybe you're just enhancing another module's capabilities. If that module is not there, nobody's going to use your code anyway. So you don't have to really require it. And optional dependencies are about the latter too. So for adapting code, imagine you have this use case that you have a user library and maybe it has a certain limitation on how much parallel users you might have, or some other reason that this library is not present in each of your deployments. But your code knows about that. Your code is aware of that, and if the class or the jar is not there, it reacts and does something different. As an example, let's say the surprise factory implementations, quote factory and chocolate factory, let's say they don't have to be there all the time. Advent can adapt, and if they're not there, it still works. So it would look like this. Note that I split the factories module into two modules. This is basically the same graph, but the dotted arrows from Advent to the factories show that I don't really want to necessarily use them. If they're there, I'm fine. If not, I'm fine too. It's the first use case, so you're adapting to the absence. The second one is you want to enhance a module. So let's say you have a usability library internally, where you collect all kinds of stuff that makes Guava better, or whatever library you're using. If nobody's using Guava, nobody's going to call your Guava enhancing code anyway. So as an example, I created an uberlib, which is totally awesome and works with all of these, right? It improves waiver, formerly known as Java slang. As Cyclops, it's a functional programming library, and you can use it for Commons Lang, yes, and Guava. You can use it with all of these, and it's totally awesome. It's going to make all of them much better. The problem for both of these use cases is, with what we know so far, if your code is going to compile against that Guava code or against that code of the library that might be absent, if it's going to compile, then you have to require it. But if you require it, it has to be there at runtime. So you cannot really solve this with what we know right now. If you require it, it has to be there at runtime. If you don't require it, you can't compile against it, at least not easily. This was basically the point of reliable configuration, to make sure that the configuration that you compile with can be somewhat enforced to be reasonable or reliable, and can also be enforced at runtime, at launch time, that it's reliable. So that's kind of the whole point, but here it makes things difficult. So there's another keyword you can throw in there. It's static, requires static. Static in the sense of not at runtime, which is totally chaotic and dynamic, but at compile time. So A requires B only at compile time, which means at compile time nothing changes. B needs to be present. At runtime things change. If B is present, great, A reads B. If B is not present, then the application launches anyway. There's no callback that informs you that something is missing. The application just launches all the same, and now it's up to you to handle this case. So the first example where the code could adapt, we could just use require static for the factories down there. And then when we create actual factories, we could do something like this. We write a method, is module present. I'm not showing it here, but it's fairly easy to write it. That you give a string, and it checks, is that module there? And if it's there, then you use the types in that module. And if it's not there, then you have to find another way. In this case, it means we don't create the chocolate factory, you get back an empty optional. For the uberlib, we just use require static on all of these, and then we fall back onto the idea that if nobody uses Guava's types, nobody is to call us with a type from Guava. So if Guava is absent, this code doesn't get called, and we're fine. We're not doing anything else. This can just stand like that. So in summary, if A requires static B, then at compile time nothing changes, and at runtime B may be absent. And you can use that if you have code that adapts to the absence or that will never get called when something is absent. And once more, I wrote a little bit more about that. Also, now is your time for questions about optional dependencies. No? Good. Services. This is at the same time the most complicated topic, and as the other ones have not been overly complicated, this one isn't either. But it's also the most fruitful. It reuses an API that has been there since Java 6 and will make it much more prominent, I hope at least. So let's go back to the factories. I put the calendar out of here to make it a little bit smaller. But we had this use case, right? We had the advent module, which uses a surprise module, which was kind of an API. And we have the factory and the surprise and the chocolate factory, which implemented interfaces from the API module surprise. But to instantiate chocolate factory and quote factory, Advent had to require these two implementations. That's something that you don't actually want to do, because Advent is like a high-level organizer thing, and now it depends on low-level details. And ideally, we want to invert these dependencies. We want to have high-level code to depend on an abstraction and low-level code to implement that abstraction. So the leftmost arrows, these two, so that they disappear, and Advent does not actively depend on these types anymore. Different ways to do that. One is the service locator pattern, which decouples consumers and implementers of an API and puts like a service registry in the center, which negotiates between someone who provides an implementation, someone who consumes an implementation. So that means that consumers and users inform the registry that they use or provide a service, and then the registry can be called and hands out instances. In the platform module system, this is done by the service loader. The service loader plays the registry since Java 6. So this is not a new feature. But the module system makes it very prominent, because modules can declare that they use a service, or they can declare that they provide a service. And then you use a service loader to load those. And this is how it looks. A will say it uses some service, fully qualified class name. And the providing module will then say, I provide that service with this concrete type. Then there are a couple of ways, a couple of requirements that type has to fulfill. The easiest one is it has to implement service. It has to have a parameterless public constructor. So now now A never sees these providers. It doesn't have to, at least. It doesn't have to see modules like B. The module system can pick up all the providers and can hand it to A by a call to the service loader down there. So A never requires B. If it wants to have instances that implement its service, it goes to the service loader, says load service class, and then it gets all implementations. There are a few more things that you can do with the service loader that are quite interesting, but we're not going to cover them here. For the factories, this is what it looks like. So now Advent says I used surprise factory, and the chocolate and quote modules said they provide that factory with the with their respective implementation. And now the module graph looks like this. Much better. So you can see that Advent does not know about factories, about the specific factory modules anymore, but only depends on the API module. It is not uncommon that Advent and Surprise are actually the same module. That a module says, I own the service interface, and I want to use all implementations. You can see that a number of times in the JDK itself. Maybe the best example is the Java SQL module, which says, I need a JDBC driver. It contains that interface, and it also says it uses the JDBC driver as the, was it Java SQL.driver class, I think. And then MySQL can implement that. So how does the use case look like in this scenario? The list of surprise factories, we used to create them by instantiating concrete types. Instead, now we go to the service loader, tell it to give us all surprise factory classes, and then some technical details. We have to start a stream. We have to do this map operation they're not going to go into, and then we're going to collect all of them into a list. So this replaces the concrete calls. So in summary, services help decouple consumers and providers. Consumers declare that they use a service, and providers say they provide a service with a specific implementation. And then the module system plays the service locator in the middle, which you can request instances from a service from. So this has a variety of use cases. One of them is, for example, that you can break circular dependencies. If you have a small module, sorry, if you have a big module and you would like to break it up in smaller modules, then it sometimes happens that everything is almost perfectly fine, but there's this one circle that you cannot break up. If there's no other way, then services could be a good solution. You could break this up by having, instead of a circular dependency, have one API module at some point, and then have two other modules depending on that one. So you can invert the dependency in one of these arrows. This is one use case. Another one is obviously to make your application more extensible. Maybe you're writing a desktop application that connects to all kinds of social networks. And then you could consider you have one Twitter implementation for your API and one, for your visualization, for your maybe JavaFX UI, and one for Google+, and one for LinkedIn and stuff. And then, depending on which service providers are available at runtime, or I have to say at launch time to be specific, then only those functionalities will be available in your program. Which brings me to the last point. It is at launch time that these services are, let's say, service binding is the official term. Let's say this is the point where they're discovered and put into the module graph, which means you cannot change this dynamically at runtime. You cannot at runtime be like, oh, I want to use that jar over there and use that service as well. With decent amounts of programming and creating your own class loaders, you can do that in Java 9, similar to how you did it in Java 8. But by default, services are not dynamic, like in OSGI, for example. That's important to keep in mind. Do you have questions about qualified exports? Sorry, my fault, about services. Services.
What if model require two different services with one type? So maybe I need some but two different realization.
So if you use a service, you say I use
something like qualifier in Spring.
You think like you want to select which implementation you get, something like that? So yeah, that was okay. So there are different ways to do that, and this call here to the provider can help you there. So provider, for example, you can use to scan for annotations. That's one way. Another way is to do that on the implementation side and have your services not be the actual service that you want to use, but a factory for your service that you can ask beforehand, like, are you the right service? Are you the one I want to use? For example, the Image.io API does that. The Image.io API internally uses a very similar infrastructure to this, not the same one, but a very similar one. And it uses, it loads all image decoders, and then asks each one, look, I have this image stream. Can you decode it? Can you decode it? So it gets all services, asks them whether they can decode the specific image that they have, and if one of them says, yes, I can, then that service gets used to instantiate the actual decoder that is going to be used later. So it's not the decoder that is the service, but something that is a factory for the decoder. That would be another way to have something like that, to select the specific implementation you want. But the service system, the services per se don't provide an easy way to do that, or a straightforward way. You have to implement it yourself, or use annotations. Okay, now I want to go to qualified exports. So far, we've covered exports, like in the beginning, right? I export a package, and then everybody can use that package. Now, maybe you want to share code in a package across all of your modules, because you deploy, let's, for example, you're developing Spring or something similar. You're going to have more than one module, and you might have code that you want to use only inside those modules. Speaking in JDK terms, maybe you have a class like sunMISC unsafe that nobody outside is supposed to use, but everybody within the JDK is supposed to use. As far as we know, this doesn't work yet. So this is similar to the problem with utility classes. Before Java 9, if you had a utility class that was supposed to be used from several packages, then you had to make it public, which meant everybody can see that class. This is very similar now. If a package should be visible outside of a module, it needs to be exported, which means everybody can see it. The module system fixed the former problem by allowing us simply not to export the package that contains that public class. The latter, there's a solution too. It's called a qualified export, and when you export a package, you say which module or modules you want to export it to. So in this specific example, B can access some package just the way as if it were regularly exported, but no other module can. So A can control who can read this specific package. So let's say you want to create something that makes it easier to implement surprise factories. We realize there's like 8 methods in there, and 6 of them always look the same, and they don't work with default methods, because that would be the better solution. So we maybe need like an abstract class, like abstract surprise factory, that we want to use internally across the different factory modules, but we don't want to maintain those in the long run, because it might change. So we don't want to maintain that one in the long run, the abstract surprise factory. So what we could do, we could put it into a specific package. It has to be a new package, right? If it goes into a package that is already exported, then we're done. But if we put it into a package that is not regularly exported, then we can say we export factory to, and then we list the other modules we want to export to. And I think without a space, but hey. So in that case, only chocolate and quote factories can read this, can access the classes in that package. So that's pretty simple. With A exports package to B, then only B can access it and everybody else can't, just like before. And with this, you can share code in a package within your set of modules that you want to define. Reflective access. It's very similar, so I want to do it at the same time. You can have questions about both. That's really interesting when you think about something like Spring or Hibernate, because you have code that reflects over your code. But maybe you don't want to make those packages exported. Remember, exported always means public API. You're going to support that, which in a large enough application might mean that at some point somebody else comes and says, why did you change those classes? I depended on them. And you realized you shouldn't have exported them. With what we know now, you have to export a package for it to be accessible at runtime. So for Spring and Hibernate to use it, you would have to export it, make it public API. But specifically for reflection, there's an alternative. It's called an open package. You don't export the package, you open the package. At compile time, it's encapsulated just like as if there were no export. Well, there is no export, so it's inaccessible. But at runtime, it can be reflected over. And even more than regular exports, you can use reflection to go deep into these classes, including private fields. So if you reflect over an exported package, you can still only use the public members. If a package is opened, you can use reflection, you can so-called deep reflection to all the set accessible true calls that show up in those code lines. And also a qualified variant that says opens to exists as well. So you can open a package to a specific module. And if all of that is too much work, and specifically when you're just starting with your modularization, you might consider creating open modules, which just say, basically I say, screw accessibility, I'm just going to open and export everything that I have. So that is like maybe a first step if you're developing an application. I would never, as a library developer, you should never ship such a module, because then people start using the stuff that later you might realize you want to keep internal. So with open modules or packages, you can make, code can be made accessible at runtime only. That's wrong. It should say runtime only. And this is particularly important for reflection. Okay, do you have questions about exports to and opens to and open modules? Okay, we have like a couple minutes left.
I have a
sorry.
Have a question. Is there any benefits to move to this new model subsystem with an existing project?
Okay, so I only got parts of that. The question is what are the benefits to move to? Okay, what are the benefits of the module system?
Is it like possible to do it, and is it harder? Or?
Okay, so the second question, is it possible? So the first question, what are the benefits of moving to modularization? One of the things I'm going to show you later, actually, it's Genling. You can do some cool stuff with that. I would say the benefit is that you now have much more control over what your code's API is. You can much more deliberately decide how to design your system than you did before. Because especially when you work in a large code base, if I use some type, as soon as the IDE says, hey, you need an import for that, I just hit Alt-Enter, have that import, and it's done. And at least in my projects, nobody ever really carefully reviewed imports, because there were just too many. With this, it's different. I hope it's different. I'm sure it will be, because the module descriptor is much more compact. Somebody during a code review could check, like, do you really want to use that module? Do we want that we establish this dependency? It's condensed, and it's much better to review and to decide deliberately how to form your dependencies. If you're a library developer, then strong encapsulation is just plain awesome, I think, because you can make sure nobody uses your internal code. And already now some features creep up in IDEs that support modularity by drawing module graphs, for example. So I assume that more tools will have proper support for modularity, making it providing further benefit using that. Regarding the question whether you can do this slowly, yes, you can, but I can't cover that in this talk. I have a source for you later that you can purchase. I want to talk about command line options, but I'm going to skip that and talk about runtime images to give you something that you can, really cool thing, I think, that you can do. So I'm sure you remember this graph and all the details in there. So let's benefit from that. Let's benefit from the JDK modularization. Because what you can do, you can create a JDK runtime image, which looks like a JDK install, with just the modules you need. So first of all, you have to know which modules you actually need. And you could use JDEPs for that, which I'm not going into now. But then the second step is you can create a runtime image with just those modules, which you do with Genling, which I'm showing you now. So Genling is a new command line tool, which ships with JDK 9. And the most basic use is this one. You define an output folder where you want to have your new runtime image. You need to specify where the modules are that you want to use. And it does not automatically read the modules from its own JDK install. You have to actually specify them. Oh, the underscore looks interesting. So you have to actually specify where these modules come from. And then you start with add modules. You just specify which modules you want to have there. And this is the most simple example. You just put in the Java base module. And if you do that, you can go into JDK, in the folder, go into the bin folder, and execute the Java command and ask it to list the modules it contains. And lo and behold, it says it only contains Java base. This drops the size of the JDK image to, I think, about 40 megabytes, but I didn't check recently. It's fluctuated a little bit during development of JDK 9. So that's nice, I think. Now let's say you have a backend and it just randomly pulls some well-used JDK APIs. Let's say use JAX WS, JAXP, JAXB, JDBC, and Java util logging. And you know that because you analyzed your code with JDEPs, for example, and it showed you use these JDK modules. Then you could create an image which contains just these modules. So there's no reason to make 2 lines out of this. It just didn't fit in 1 line. So this way you have a module that contains not only these modules, but Genling is of course clever enough to pull in all other modules that these modules depend on. Which is why if you say list modules, you get a few more than you expected. Still much less than original JDK. Doesn't contain Java. Oh, it does contain Java Desktop. Java Desktop contains Swing and AWT. And the reasons why it's in there, it also contains the Beans API, because circular dependencies. So if you want to get rid of the Java Desktop stuff, which is a lot of classes, then you have to drop, I think it's JAX WS, which pulls it in, but I'm not sure. Still smaller than the regular runtime image, and you can deploy that. For example, first of all, if you're running on an IoT device, that might be nice, save a little bit disk space. Genling can also aggressively optimize code, because Genling has a full view of which methods are used. So it can cut unused code and can do further optimizations. In the end, you get a monolithic image, which claims to contain several modules, but really contains just these all basically compiled into one set of bytecode. And Genling is pluginable, and there will be plugins who will allow further optimization. So that's step 1. Create an image that supports your application. Why not create an image with your application? If you've modularized your entire application, including its dependencies, you can do that differently. You can say the module path is not only the JMods folder in the JDK install, it's also my mods folder, which contains my modules and my dependencies. And then you say add modules, in this case advent, so you just use the root module of your application, and services have to be added extra. So I put the other services in there too. And then it creates a runtime image with all the platform modules, with all the JDK modules, and all the application models in there too. And launching the app then means you tell Java to just launch the module advent. And because it ships with it, it can launch. Still smaller than JDK. One step further, you can create a launcher, so it's even easier to launch. You can use the launcher option and say what the option is supposed to call. In this one, it's supposed to be called calendar. And so the launch script is called calendar, and it launches the module advent. And then you can launch with JDK bin calendar, which is quite nice. More options, which I'm not going to go over. And then as a summary, once you have, well, actually that's not entirely true. So you can create a runtime image with just the right classes for every Java 9 application. Even for Java 8 applications, if they don't do anything that doesn't work on Java 9. So for the first part, you only need to know which modules you use, which will be readily available with JDEPs. But if you want to create a runtime image that includes your code and all your dependencies need to be modularized. And if you're having certain kinds of deployments, it should make these faster or easier. For example, if you're delivering a desktop app, it's now very easy to deploy that app, including everything that it needs and nothing more. So it's easier for you to not depend on the JDK install of your customer. If you develop a microservices, this shrinks the image size and makes it also easier to launch. And if you have, oh yeah, questions about Genling, of course. Okay, so I can't see any hands. So what about OSGI? Well, no time. So I said, I want to say something about me. I'm Nicolai. I'm blogging at codefx.org. I'm doing a lot of other stuff, but I'm also writing a book at the moment about this specific topic, and just finished the chapter on services. So there, I would have liked to talk much more about that. But